This is layum in for bear. Show me why the yellow square equals the blue plus the red, the way Byrne drew it in 1847. In 1847, Oliver Byrne published a proof of Euclid almost without words. He replaced every letter, every angle label, every side name with a color. Red, blue, yellow. The color is the math. We're about to watch 3 colored squares prove the Pythagorean theorem step by step. Every step is just one piece equaling another piece. 3 points. C is the right angle, that small square marks it. B is directly above, connected by the blue side. A is directly to the right, connected by the red side. Yellow closes the triangle on top, the hypotenuse AB. Blue leg, red leg, yellow hypotenuse. That's the whole cast. The claim, the yellow square equals the blue square plus the red square. Not a formula, a colored equation. That colored square to the left is the hypotenuse squared. The 2 on the right are the legs squared. Byrne's entire 400-page book is this kind of equation proved step by step. 3 squares, 1 on each side, built outward from the triangle. The blue square on the vertical leg CB, the red square on the horizontal leg CA, the yellow square on the hypotenuse AB. These are the shapes we're proving equal, not just drawn for decoration, but the actual mathematical objects in the claim. One cut, a perpendicular drops from C, the right angle vertex, down to the hypotenuse, then keeps going straight through the yellow square, splitting it into 2 rectangles. Everything else dims. This single line is the engine of the entire proof. The slope is exactly -4/3. It passes exactly through C. Now the move that links the squares to the rectangles. 2 auxiliary triangles appear, green so you can track the pair. One stretches from C across to the far corner of the yellow square. The other hangs down from the far corner of the red square to B. They look different. Euclid says they are the same triangle. Watch, the left triangle has 2 sides. CA equals 240 and the side of the yellow square equals 300. The right triangle has the same 2 lengths in the same order, and the included angles are equal. Each is the angle at +90 degrees. Side angle side. The triangle lifts, rotates 90 degrees, and lands exactly on the other one. That's the proof. After the rotation, that triangle sits inside the red square, sharing the same base and the same parallel lines as the square. Euclid I, 41. A parallelogram on the same base between the same parallels is twice the triangle. Cut the red square along the diagonal and you get exactly that triangle. So the triangle is half the red square. And before the rotation, when the triangle was still in its original position, it was exactly half of the right rectangle inside the yellow square. Same argument, shared base AA', the full side of the yellow square and the same pair of parallel lines, so CAA' is half the right rectangle. No words, no symbols, color was the notation, and the proof was watching pieces equal pieces. Take Euclid Book I, Proposition 5, the isosceles triangle. Recolor it Byrne's way, assign each line and each angle a color, then write the proof using only the colors. The question to look for: where does the color notation get ambiguous? Where does a single color have to mean 2 different things at once? That ambiguity is why algebra eventually won. It's worth finding it yourself. Take this prompt, paste it into Claude, and run it. Byrne's 47, layum.